All right, so the first thing that we're going to do is on this diode lab, we're going to make sure we have the proper power to our board. So I have a power supply. According to the power supply, it's putting out 9 volts. And I have on my board, I've created some small loops that will allow me to carry on the circuit. This breadboard, you'll notice that the blue and red buses in all of these have a break in it, and that basically means that the bus stops here, does not continue on. So if you're using a board like this, you've got to remember to put a bridge or a jumper or a branch or whatever wire you want to call it between the two halves so that it runs right through, and the same goes for our power rail. So just to confirm, I'm going to check my voltage, and it's saying I've got 9.1. The power supply is saying I've got 9. So I can fine-tune that. Let's see if we drop that exactly down to 9. A little lower. .05, so that's pretty darn close. So we're going to use that as our power supply and supply to the bus or to the breadboard. So the next step is to start putting our pieces on our breadboard for the lab itself. All right, so I've got here a very small jumper wire, and you can actually buy these pre-made. The good news is that they're really handy to work with because they're small, they're already formed, they bend in a nice right angle. They make great little jumpers, like I could have used them like that. They're really handy. The problem with them is that, unfortunately, it's the most expensive way you can buy wire. For what they are and how much they cost, it's quite prohibitive, but they do the job. If you were working on a breadboard, and I'm just going to give you an example, and you had to use these big hoops, you quickly lose sight of where they're coming and going from, and that is mission critical when you're working on the board because everything's tiny and you're trying to figure out where the circuit's going. The other thing, this however does have an advantage if you're measuring current through the circuit. You'd want something like this if you have one of those Hall effect clamp-on meters that you've been issued and you want to measure the current. That's the best way to do that. The current's going to have to pass through it to get from one row to the other. Okay, so I'm going to start putting in some LEDs as per the print. And the thing about an LED is that it does have a positive and a negative, an anode and a cathode. But the problem is making sure you know which is which. Now, if you happen to have an LED and you hold it straight up, you can see that there is a flat side. It's really, really hard to see for middle-aged dyes like mine, but it does tell you there's a flat spot on one side of the plastic casing. A simpler way is that's the fallback position. I'm going to say that. That's the fallback position if somebody's trimmed the leads and you're not sure which is which. The advantage is, of course, that the longer side, it actually, think of it this way, that, if they added some wire, they'd have to use addition, which 1 plus 1 gives you 2, so that must be the plus side. And this one, they subtracted some, they made it shorter, so that's a minus sign, so that's got to be negative. Now, what I do whenever I have a brand new LED and I'm going to be using it, the very first thing that I do is I take the anode, the positive lead, and I bend a knee in it. Now, it does two things. One, by bending a knee, you can see that the leads are now pretty close to being the same length. So when I go to insert it in my board, the presentation of the LED is going to be straight. It's not going to be leaning one way or the other. The other thing it does is this knee tells me that's my anode, because once you pull it in and out, what ends up happening is they can look the same but not be the same. And this, I always think of it this way. This is I'm bending a knee, and if you ever were to, be presented to the king or queen to be knighted, etc., then you would have to kneel, and then they go put the whole sword thing and you arise. So I'm kneeling to power, so that's going to be my positive, and I'm going to start up here on the top, and I'm going to cross the moat, and there's my first LED. And notice it's now sitting square, and you can see exactly what it's doing. And I'm going to put one beside it. Now, ideally, you'd like to get them all on the same rows, but you may not have the room. Bend my knee. I got 2. And then we get the full traffic light effect. Bent knee. Huggy bear around the other ones, and now I've got three as a cluster. So to review, I've got 9 volts coming in. It goes through my 100 ohm resistor, goes into the back plane. There's a switch interrupting the circuit. I come out, and so does my switch. Put that back in there. Okay, so there's my switch, in and out of my switch, through my jumper lead to this row. These are all my anodes, these are all my cathodes, so now the only thing I need to complete my circuit is my diode, the other diode we're going to use, and then eventually finish that. Okay, I've turned the power off of the circuit, and the part 1 starts talking about, in the lab, starts talking about taking some measurements. So it says connect the diode to your breadboard. That's done. Place the red lead on the positive, so we're going to put the red lead over here. That's our positive side of our diode. This is our negative. And we're going to use the black lead on the cathode, like so. So what we're going to do is we're going to measure the resistance. So I'm going to set my multimeter to resistance. Now this is an older multimeter, and when you're working with older multimeters, this particular one is not auto-ranging. What do I mean by auto-ranging? Your meter is auto-ranging. When you measure resistance, it starts out with the lowest or highest value. I can't remember. I think yours starts with the lowest and works up to the highest. So it starts out with milliohms, then it goes to ohms, then it goes to kiloohms, then from kiloohms it goes to mega ohms. This goes up to 2000 K ohms, which is 2 mega ohms, 200 K ohms, 20 K ohms, 2000 ohms, or 2K ohms, and then 200 ohms maximum. So I have to select the right one. Now normally what you do, if you don't have an auto-ranging one, you start with the highest and work your way lowest. Simply because you can start from the lowest and work your way higher. That's perfectly acceptable. But I've just always made it a habit, start high and work low. So I've got these two here, and right now it says it's 292, and I'm on meg ohms. Let's just move this down to say 20 k ohms and see what I get from my reading. 7.64. So let's take that down to say 200 ohms. Now, as soon as it has the 1, it says, yeah, I can't read that. That's not enough. Okay, let's go up to the next one. Still can't read it. And now it's giving me about 500 ohms of resistance. So on that first question, where we're asking for the measurement, you can say that it's got 500 ohms of resistance. Let's just move it up another one to see what it says. .2. This is working correctly. Let's check our 100 ohm resistor and see what it gives for 100 ohms. And we can see the decimal place has moved. And it goes, yeah, that's too much. Let's kick that down. That says exactly 100, so that's the correct range to use. 99, 100, perfect. So 500 ohms would be the correct response. Just because it's not auto ranging, I have to have a reference and then I know which range to use if you're not sure. Because you saw that this was bouncing about, and as I've explained before with all meters, read the manual, understand what it does. They don't all behave the same way. You see a number 1 here, that could mean anything. In this particular case, it means that it's outside of its limits. You've gone way beyond, I don't know what it is. There's nothing else on the screen. Okay, so we know that that's 500 ohms. So then what we're going to do is we're going to reverse our leads. So now I've got the red in my left hand and the black in my right hand, and I'm going to measure again. And I'm at 200 ohms. Let's just check this. I still have 100. Notice that we don't have a polarity sign on this particular meter. Okay, so I'm going to do this. Resistors don't have polarity, but if you're testing DC power, that is going to show you a negative and positive. So here it says, oh, that's outside of my range. Okay, let's drop down one. Still outside of my range. Okay, let's go back up. Still outside of my range. Still can't read it. Still can't read it. So it's, for this, it's outside of its capability of even reading it. So on your meter, if it could not find a value, it's going to give you that O and L saying that it is an overload protection. In other words, we can't figure it out, so we're shutting down. I like to say there was a manual on one company that OL stands for outside of limits, either up or down. It was either too small or too high. It couldn't decide what it was doing. So we know that this, in this case here, that on your meter it would be an OL, and that tells us that I've moved all the way up to 2 meg ohms, and it still can't determine how much resistance is there. So notice that it can't tell now just the leads touching. So that indicates whether it's, if it touches and I get 0, that's a very low reading. If it has nothing, that's a very high resistance reading. All right, so I've now installed the other diode, and you can see there is a little silver streak here on the one side. That indicates the cathode, the negative most part of the circuit. It goes to my negative bus, which goes back to the power supply. Now this particular diode is a 4007, and it is a very popular diode. It's an IN4007. It's a great robust diode. They still manufacture them. they've made them for, it seems like forever, but at any rate, they're a very robust diode. Diodes originally, before they found out about the doping, were vacuum tubes. And they had a plate, and it was inside a vacuum, and they would charge up and warm up one plate. The plate would then start emitting, the anode would start emitting, and the cathode would pick it up, and current would only flow in the one direction. And that was handy to start converting alternating current from Mr. Tesla to direct current vis-a-vis Mr. Edison. So let's see, we've got this all set up. I've got just double checking, my button's in the right place. Going to turn on the power, make sure I've got the appropriate amount of power here. And I've got my 9 volts. Excellent. So when I press this button, the LED should come on. So I know that I've got a complete circuit, and it must be going through this diode as well, because otherwise these lights would not light up. They're not right to the negative bus. So now that I've done that, I can now take some time and connect up start to use the oscilloscope to see what happens to the waveform as it goes through the circuit. All right, now if you had a defective blown diode, you would have the number 1 on this model, but on yours it would have an overload on both sides because it's an open circuit, it can't read it. So the next part we're going to do, I've changed the setting now to where it says, I have my arrow stuck in the wall, that's the diode symbol. In this case, it does double duty, it does continuity, and it also does the diode. So now I've got to make sure I put my red lead back into my right hand. One thing to keep aware of before you do any measurement, and I'm doing this right now behind the camera where you can't see it, when you start swapping, you'll tangle your leads. Before you take any measurement, make sure that the leads aren't going to trip you up. And by that I mean that you're taking a measurement and the next thing you know you've got the wrong leads in your hands. Always make sure that they're clear and they're not going to present their own hazard. So I'm going to put the negative lead on the cathode of our diodes. And on a diode setting, what it's going to do is it's going to produce a voltage that should trigger the diode. And I've got the red one going, and the green is back here. Only seems to have enough power to turn on one. So this one is taking up the vast majority of the available power. But when you put it into diode mode, it's actually sending out a voltage enough to turn on an LED or enough to power a diode, detect the diode in the circuit. Okay, one quick note. If you're checking a diode, I had the power turned off. I forgot to mention that. If you don't want to be trying to test a diode using your meter at the same time you've got power into the circuit, it's assuming that the circuit is turned off. If you don't, you're now putting your meter at rest at worst. Well, there's one thing that's going on. The other thing you're doing is you're actually adding to the circuit. You're applying an extra voltage on top of the voltage that's being applied because you're in parallel. So make sure that there's no power on, and the best way to do that is to take a lead off. Now I had the power supply turned off, but you can't see the power supply, so you'd have to take my word for it. I promise I did that. Don't work hot. So now we're going to move on to the next test. We're going to find out what the voltage drop across each of these resistors are. So I'm going to change the setting to the lowest voltage I've got, in which case is 20 volts DC on this meter. And I'm going to turn on the power side, be right back. Okay, one quick note. If you're checking a diode, I had the power turned off. I forgot to mention that. If you don't want to be trying to test a diode using your meter at the same time you've got power into the circuit, it's assuming that the circuit is turned off. If you don't, you're now putting your meter at rest at worst. Well, there's one thing that's going on. The other thing you're doing is you're actually adding to the circuit. You're applying an extra voltage on top of the voltage that's being applied because you're in parallel. So make sure that there's no power on, and the best way to do that is to take a lead off. Now I had the power supply turned off, but you can't see the power supply, so you'd have to take my word for it. I promise I did that. Don't work hot. So now we're going to move on to the next test. We're going to find out what the voltage drop across each of these resistors are. So I'm going to change the setting to the lowest voltage I've got, in which case is 20 volts DC on this meter. And I'm going to turn on the power side, be right back. All right, so we're now going to actually apply power to our circuit. And if the circuit is wired correctly, when I push this button, the light should come on, which they do. Excellent. And when it turns on, because the power is going from positive through our resistor into the backplane, across the backplane to the switch, to the next row via the switch, into the backplane, through our jumper, back into the backplane, out of the backplane, into the anodes of all three LEDs. The cathodes all go back into the breadboard onto a new row on the opposite side of our moat, and it then goes in the backplane to our other diode, through that diode to our negative anode bus, or a cathode bus, pardon me, and supplying the circuit. So if the light turns on, then it must be in forward bias. So if I then turn around, I'm going to turn the power off for safety first. And I'm going to turn this around, and I'm going to reverse the bias of the diode. Put that in there. Again, you can see the silver is on the other side. All right, so I've got this hooked up to the oscilloscope, and I want to see how much voltage is actually being put out through the signal generator via the scope. And last time I did this, I came up with 14 volts, but I just want to see what the actual voltage output is. So I'm going to put my negative and my positive, and I'm at 200 volts, or 200 volts AC, and it's putting out 7 volts. Now if I look at my input, output, that's cranked up, my other output's cranked up. So the most that's going to be putting out is 7.6 volts. I'm not sure I got 14 before, but learning has occurred. A little more than 7.5 volts. Good to keep in mind. So when we look at our sine wave, we now know that because I took the meter reading, that we have 7.5 volts peak to peak, because I've maxed out my voltage output from the power supply. All right, so I've got this hooked up to the oscilloscope, and I want to see how much voltage is actually being put out through the signal generator via the scope. And last time I did this, I came up with 14 volts, but I just want to see what the actual voltage output is. So I'm going to put my negative and my positive, and I'm at 200 volts, or 200 volts AC, and it's putting out 7 volts. Now if I look at my input, output, that's cranked up, my other output's cranked up. So the most that's going to be putting out is 7.6 volts. I'm not sure I got 14 before, but learning has occurred. A little more than 7.5 volts. Good to keep in mind. So when we look at our sine wave, we now know that because I took the meter reading, that we have 7.5 volts peak to peak, because I've maxed out my voltage output from the power supply. Okay, so we've made a new circuit, and it looks sort of like a parallel circuit, but it's not. If I were to straighten these two out, let's just do that, move that over there, move that over there. Sort of like that. It looks like we have a parallel circuit. But there's two things going on. First of all, this format is known as a bridge rectifier, and it's also known as a Wheatstone bridge. If I were to make this exact circuit, which I will, if I were to make that circuit and apply voltage to it, if all the resistors are identical, and I'm using all 100 ohm resistors, and I were to take my meter and read the detected resistance, let's keep the gold bands in the same direction. Okay, so when I've done this, if I were to take a meter and read from this point to this point, if these four resistors are identical, then what ends up happening is there's no potential difference between these two legs. So putting a meter across here, I should, in theory, read 0. So in this case, the current's flowing in one direction, but because both lines are the same, it's basically just a current voltage divider combination. It's not, there's nothing super fancy about it. In fact, you can say it's just basically a parallel circuit of two 100 ohm resistors. But in this configuration, the current's got a lot of working to do to finish and complete the circuit. So if we look at it and say that we're going to use conventional flow, so if the current goes through, it can't go this way, it's blocked because that's reverse bias. So it goes into this resistor. It wants to go here, but it's got a roadblock because this diode is reverse bias. So then it goes across the resistor, finds its way here, and then it goes through the power supply, but it comes back on this leg, it comes back on the negative on the next rotation of the waveform. So then it's going to enter in here, can't go there, that's reverse bias. So as it goes across here, can't go this way, because that's just a loop, so it's going to go this way to finish the circuit. And by doing that, what ends up happening is the current is flowing backwards and forwards across here, and you get one half of the waveform from this direction and the other half of the waveform from this direction. And you end up with a full wave rectifier. Now, an interesting thing that happens along the way, we'll just put this across the load. We'll see what our... Okay, so when you look at the screen, a lot of times you will find that you do not get a full wave. You get this half wave. And I've done some research on that because I've had other signal generators and I've had other oscilloscopes, and it's never been a problem. All of these are duplicated. But here I don't have that. I have this space. And it has to do with the reference ground between the function generator and the oscilloscope. And I don't have a probe to... these alligator clips are not giving me that proper signal. If I had to ground off one of the probes, then I should be able to... I believe it's the probe you have to ground off, and then you get the wave. When I've done it on my old oscilloscope, it comes up perfect with the probe every single time. But I wanted to show you that this bridge rectifier works, and you just have to imagine. I might do some photo editing to give you an idea of what that looks like. There's still gaps, there's still little dips, so it kind of oscillates, and when you get into level 2, you'll build a successful one, and you'll use some other devices to level that off, and then you get a true DC full rectification.